Hello everyone. Today we will discuss DFA, NFA and NFA with null moves. So DFA stands for deterministic finite automata, NFA stands for non-deterministic finite automata and NFA with null moves stands for non-deterministic finite automata with null moves or epsilon moves. So we'll discuss here formal definition, transition diagram and transition table for each finite automata one by one. So first we will discuss deterministic finite automata. So here we'll discuss formal definition of DFA. Formally, a DFA can be defined using 5 tuples. 5 tuples are capital Q, sigma, delta, Q naught and capital F. Capital Q stands for finite set of states. For example, a DFA is having states like Q0, Q1, Q2 up to Qn, mean n plus 1 states are there. So it can be written in form of set like this. Input alphabet sigma equal to, for example, A comma B. Now Q0 stands for start state and Q0 is member of capital Q. Capital F stands for set of final states where capital F is subset of capital Q. Now we'll see definition of delta. Delta stands for transition function. Transition function shows mapping of capital Q into sigma to capital Q. Mean from current state for current input symbol will move to next state. So here we will discuss the properties of DFA, informal meaning of transition function or properties of DFA. So in this is one example of DFA. It is having 3 states Q0, Q1 and Q2. How it is DFA? Mean for particular state, for particular input symbol, there should be only one transition, first property. Now second property, for particular state, there should be outgoing transition for all symbols in alphabet. Here in alphabet symbols are 0, 1. So here we will check at Q0 we have outgoing transition for 0 as well as outgoing transition for 1. At Q0 we have outgoing transition for 0 as well as outgoing transition for 1. At Q2 we have outgoing transition for 0 and outgoing transition for 1. Now again I am repeating, in DFA for particular state there should be outgoing transition for all symbols in alphabet. Second property, from particular state for particular input symbol there should be only one transition. Mean at Q0 for 0 there should be only one transition. So at every state we can say for 0 and 1 there is only one transition. Here again for 0 and 1 there is only one transition. At Q2 for 0 and 1 there is only one transition. So this is DFA. Now we can plot its transition table. Now transition function shows Q into sigma. So here we will mark set of states and here we will mark input symbols. States are Q0, Q1 and Q2. So here we will write Q0, Q1 and Q2. Now next states for input symbol 0 and next state for input symbol 1. Now we can fill this table accordingly. At Q0 for input symbol 0, next state is Q1. At Q0 for input symbol 0, we can write here Q1. At Q0 for input symbol 1, next state is Q0 due to this self loop. So at Q0 for input symbol 1, we can write Q0. At Q1 for input symbol 0, next state is Q2. So at Q1 for input symbol 0, next state is Q2. At Q1 for input symbol 1, next state is Q0. At Q1 for input symbol 1, next state is Q0. Now at Q2 for input symbol 0, next state is again Q2. At Q1 for input symbol 1, next state is Q0. At Q2 for input symbol 1, next state is Q0. So in that way we can plot the transition table for DFA. Now next is NFA. NFA stands for non-deterministic finite automata. Again, it can be defined using 5 tuples: capital Q, sigma, delta, Q naught and capital F. Capital Q, as we discussed in deterministic finite automata, capital Q stands for finite set of states. This is input alphabet. This is a start state. Capital F stands for set of final states. Now difference lies in definition of delta. So here delta means transition function. In NFA, transition function is defined like this. That is Q into sigma to 2 raised to the power Q. What is the meaning? From current state, for current input symbol will move to one of the element of power set of Q. Right. So here we will discuss the meaning of power set of Q. Just see one example. Suppose Q is equal to, there are two states like Q naught and Q1. Right. So now we need to obtain power set of Q, 2 raised to the power Q or power set of Q. So it can be obtained like this. Power set of Q mean all possible subsets of this set. All possible subsets of this set. So it can be written like phi. Another subset of this set is Q naught. Another subset is Q1. And next possible subset is Q naught comma Q1. So it can be written as all possible subsets of given set. Right. So function is capital Q to sigma to 2 raised to the power Q. Now we'll see one example to better understand the definition. Now suppose we have regular expression as a plus b whole star ABA. Right. So we can easily plot non-deterministic finite automata. This is suppose our start state. And here we have a plus b whole star. So here we can easily mark a self loop for input symbol a comma b. Now next is this is followed by ABA. So here we will mark a state for input symbol A. Next we will mark next state for input symbol B, concatenated by A. So again we will create a new state and here we will mark transition A and this should be final state. Now we can give name to the states like Q0, Q1, Q2 and Q3. Now see here in NFA from particular state for particular input symbol there can be 0 or more transitions. So in NFA choices are non-deterministic in nature. For example, at this state at Q0 for input symbol A there are 2 outgoing transitions. One transition is leading to state Q0 itself. Second outgoing transition for input state A for input symbol A is leading us to state Q1. So now here we can say at particular state for particular input symbol there will be 0 or more transition. For example, at Q1 for input symbol A there is no transition. At Q2 for input symbol B there is no outgoing transition. At Q3 for A and B there is no transition. So this particular finite automata is called as non-deterministic finite automata, where from current state for current input symbol will move to any one of the member of power set of Q. Now we'll see how to draw transition table for NFA. So a transition table can be drawn like this. That is, again it will be derived through this function only. First is Q. So here we will write the states in NFA that are Q0, Q1, Q2 and Q3. These are the states. Now second is alphabet. Alphabet is A comma B. So here transitions are marked for input symbol A and B. Now we will mark the next states in these cells. So next states are one of the member of power set of Q like this. So now we'll see this diagram at Q0 for input symbol A, next states are Q0 and Q1. So here we will write Q0 comma Q1. Here we will write
one of the member of power set of these states q0, q1, q2 and q3. So q1 comma q0 comma q1 is member of power set of these states. Now at q0 for input symbol B, next state is q0. So here we will write q0. We'll write everything in form of set, because in power set we'll write elements in form of sets. At q1 for input symbol A, there is no outgoing transition, so we will write phi. We know phi is member of power set of states. Now at q1 for input symbol B, next state is q2. So here we will write q2. Now at q2 for input symbol A, next state is q3. So here we will write q3 in curly parenthesis. Now at q2 for B, there is no outgoing transition. At q3 for A and B, no outgoing transition. So here we will write phi. So what this table is showing, from current state for particular input symbol, the next states are taken from the members of 2 raised to the power q. Here we will write the members of power set of q. So everything will be written in form of sets. This is empty set and these are the elements of power set of q. So this is the table for non-deterministic finite automata. Now we will focus on non-deterministic finite automata with null moves. Again, it is defined using these 5 tuples. Capital Q stands for finite set of states. This is input alphabet. Q0 stands for start state and capital F stands for set of final states. Now again, the difference lies in the definition of delta. So in NFA with null moves, definition of delta is like delta is defined like Q into sigma union epsilon to 2 raised to the power q. So it shows from current state, for current input symbol or epsilon move will move to any of the member of power set of q. Right. So the difference is the transition will be marked either from symbols from alphabet or using epsilon. Now see this particular example. Here we are having states from q0 to q5. q0, q1, q2, q3, q4 and q5. Here some transitions are marked using epsilon. So from q0 for epsilon, next state is q1. At q1 for A, next state is q2. So here we will see this is a transition where epsilon is marked. So transitions will be marked from symbols from alphabet. Here alphabet is equal to A comma B. So A comma B, A or B can be marked on the transitions, or transitions can be marked through epsilon, null moves. What is the meaning of null move actually? Meaning of null move mean in state diagram will move from one state to another without reading any input symbol. Right. Now see 2 raised to the power q mean choices are again non-deterministic in nature. It means from particular state for particular input symbol will move to 0 or more states. For example, here at q0 for input symbol A there is no transition. At q1 for A there is transition, but for B there is no transition. Now we'll focus how to draw this transition table. Again, this transition table is derived using this function only. Now see here, present states are capital Q. So here we will write all states of this transition diagram. States are Q0, Q1, Q2, Q3, Q4 and Q5. So here we will write all states. Now next is alphabet union epsilon. So here we will create columns for symbols in alphabet. In alphabet symbols are A comma B. So we have created 2 columns, one for A, second for B. Now here we have epsilon also. So mean on transition can be marked on epsilon move also. So here we are creating 1 column for epsilon also. Now 2, this is 2 raised to the power q, mean in these cells we will write members of power set of q. Right. So now see at q0 for input symbol A, there is no transition, so we'll write here phi. For B, there is no transition, so we'll write here phi. Now, for epsilon, there are two states. So, states are Q1 and Q3. So, here we will write element of power set of Q3 like Q1 comma Q3. At Q1 for A, next state is Q2. Now, at Q1 for B, next state is phi. For epsilon, phi. At Q2 for A and B, phi, no transition, and epsilon next state is Q5. So here we will write Q5. At Q3 for A, no transition. For B, next state is Q4. At Q3 for epsilon, no transition. Now at Q4 for A and B, no outgoing transitions. So here we will write phi. At Q4 for epsilon, next state is Q5. So here we will write Q5. At Q5 for A, B or epsilon, there is no transition. So here we will write phi. Right? So in that way, we can draw transition table for NFA with null moves. Now we will see the processing of input tape and finite control, how they work together. Now this is the input tape. Input tape is divided into number of cells, and these cells are marked using small case Roman letters, first, second, third and so on. This is left end and this grows at right end. Now this is the finite control where we'll have finite automata. Any finite automata will be residing here. Now input tape and finite control units, they are linked using the head pointer. So this is the head pointer. Now in finite automata, head pointer has these three properties. Properties are head pointer can move in forward direction only, mean it will move in this direction, left to right only. Now this pointer is read only pointer. Read only mean head pointer can read the symbols from the tape. It cannot write anything onto the tape. Now one symbol at a time mean head pointer will read one symbol at a time. So property is it will move from left to right and it will read one symbol at a time. Now see how these two units work together. So here on tape, suppose we have input string like A, B, A, B, A, A. And this is suppose the finite state machine, start state is this, final state is this, and some transitions are marked over here. Now see, initially head pointer will point to cell first, and in state diagram triggering point will be at start state. Now here the input symbol is A. Now through head pointer will read input symbol A. Now at start state for input symbol A, next state is capital B. So here in state diagram will move from capital A to capital B. Now in head pointer, after reading small a, head pointer will advance one cell to right. Now head pointer will point to cell second, and here will read the next symbol, that is small b. Now here we have at state capital B, symbol is small b. For symbol is small b will move to state capital C. Now head pointer will advance one cell to right. Now it will point to cell third. Now at cell third symbol is small a. Now after reading small a will move to next state. Right. Now here head pointer again will advance one cell to right. Now head pointer will point to cell fourth. Here symbol is B. After reading B will move to next state. So in that way head pointer advances from one cell to another cell, and here will move in a state diagram. So here we move from one cell to another cell, and here will move from one state to another state. So here will move state by state, here will move cell to cell. So this is the processing. How we'll say a particular string is accepted. If the entire tape is dead, mean we are at end of the string, like next symbol is blank or we are at end of the string. and here we have reached one of the final states of finite automata. Then we'll see that the string is accepted or tape is accepted, otherwise we'll say that a string is not accepted. So this is about the processing of input tape and finite control unit. Thank you.